All right. All right. I'm also looking at the YouTube channel thing, like I have the link open, and I don't see. All right. I'm also looking at the oh, now I see it. YouTube channel thing, like I have the link open, and I don't see. All right. I'm looking at the YouTube channel thing, like I have the link open. We'll get started. And I don't see. All right. I'm also looking at the oh, now I see it. YouTube channel thing, like I have the link open. And I don't see. All right. I'm looking at the okay, hey everybody, welcome to YouTube the Emag exam 1 review. We'll get started. Let me know in the chat on YouTube if y'all can hear me. Also looking at the oh, now I see it. YouTube channel thing, like I have the link open. And I don't see. All right. I'm looking at okay. All right, so the first topic on this exam is from lecture 1. It's the vector operations. People are still saying there's feedback. Okay. All right, so the first topic on this exam is from lecture 1. It's the vector operations. People are still saying there's feedback. Okay. All right, so the first topic on this exam is from lecture 1. It's the vector operations. People are still saying there's feedback. Victor, is it better now? Okay. All right, so the first topic on this exam is from lecture 1. It's the vector operations. People are still saying there's feedback. Victor, is it better now? Okay. All right, so the first topic on this exam is from lecture 1. Okay. Let me know if it worked. Okay. Let me know if it worked. Okay. Is it sounding any better now? Let me know if it worked. Okay. Is it sounding any better now? Let me know if it Okay. I'm still screen sharing from the Notes app. Is it working? Is it working? Okay. I'm still screen sharing from the Notes app. Is it working? Is it working? Okay. I'm still screen sharing from the Notes app. Is it working? Is it working? Okay. I'm still screen sharing from the Notes app. Is it working? Is it working? Okay, people on YouTube say that it's working. I'm still screen sharing from the Notes app. Should I continue? Is it working? Is it working? Okay. I'm still screen sharing from the Notes app. Is it working? Is it working? Okay, people are saying it looks like it's working. That it's working. Nope. I'm still repeating. Screen sharing from the Notes Should I continue? App. Is it working? Is it working? Okay. I'm still screen sharing. I only have All right. How are we doing now? Is it working? All right, I'll wait for somebody in the YouTube chat to say whether or not it's working. And then maybe we're good. Okay, people are saying it's fine. All right, guys, sorry for the delay, but I guess this is a good time to get started on the review. So the first topic that y'all covered in class was vector operations, and I'm not going to go through this a whole lot, but I will have these notes in a PDF, and I'll post them all in the Discord for y'all to look through later. The first important thing that I want to note is the coordinate systems. So I'd say it's a good thing to remember these three little circles right here. Just as far as the right hand rule. So you'll see on these, if you go clockwise, you can do x cross y equals z, r cross v equals z, and such and such. And then if you go counterclockwise, then it's just negative for the result. And these are good to remember just for when you're setting up your diagrams. And then two other equations that you're going to want to know is the gradient and divergence, which is just different ways to find out properties of an equation, if it's a multivariable equation or a vector equation, and that applies in some electromagnetic property equations. And then I have some notes on the divergence theorem and the Stokes theorem, if you want to read through that later. And then the first electromagnetic engineering topic is electric charge and fields and the forces. So the first thing I want to note on this is R12 and F12. It can get kind of confusing if you don't know which way those are going. So you're going to want to remember that in at least Florence's notation, R12 is a vector going from Q1 to Q2 or location 1 to location 2. And then F12 is a force on Q2 from Q1. So you might want to remember those directions there. And then the first equation is Coulomb's law, which is a way to find the force from one point charge onto another. And that's 1 over 4 pi e naught times the two charges over the distance between them squared times the unit vector. And I like to simplify that to 1 over 4 pi e naught and then Q1 times Q2 over the distance between them cubed times the vector itself. And that's just preferable to use in most situations because when you solve for the vector from one point to another and the magnitude of that vector, you don't have to also solve for the unit vector. So that'll probably be better in most cases. And then the next thing is charge distributions, which can be linear distributions, surface distributions, or volume distributions. And then some more equations. When you're integrating anything in a spherical coordinate system, you're going to want to use this in the differential, this r squared sine theta. And then in cylindrical coordinates, you're going to want to integrate with r. And then you might want to use these equations, the surface area and volume of a sphere, and then the surface area and volume of a cylinder. Those apply in a lot of Gauss's law situations. And then when you're trying to find the force over a whole charge distribution, you take that same equation from before, and you keep the reference charge Q, and then instead of multiplying it by the other charge, you multiply it by the charge distribution, density, and then integrate over that to this being the vector from one point to another, and change this to being cubed. When did y'all lose the sound? Is it coming back? Can y'all hear me? Okay, I'll just go over the electric field again. So it's the same as the electric force equation, but you're going to take out that reference charge from before, and you're just going to be referencing the charge distribution itself, and then you'll find the electric field around it. So it's just like the equation from before, where you can change this part of the unit vector over the magnitude squared to the vector over the magnitude cubed, and then integrate over the charge distribution. Okay, next was in lecture 3, you started talking a lot more about calculating the electric field around distributions. So the first example that I wanted to look at was a line of charge that's going from negative L over 2 to L over 2 on the z-axis, and it has a linear density. So the first step on a problem like this is you're going to find the r vector from the charge density to a reference point, and then you're going to find the magnitude of that vector. So that's what this whole part is, and you're going to plug that in to this equation, which was just on the last part. And because this is a linear density, you only have to integrate in one direction, which is going to be on the z-axis from negative L over 2 to L over 2. And then another really important part of these problems is always going to be simplifying based on symmetry of the problem. And in a lot of cases, the symmetry is going to make some components cancel out, which makes it a lot easier to do the integration. So in this case, the vertical components are canceling out because any force that's coming from a point on the bottom of the line and going up, that vertical component here, will cancel out with the vertical component coming from the top of the line and going down. So you're left with just the horizontal component. And then you plug in all of this from up here into the equation, and you're going to get rid of the z components because the symmetry said you didn't need those. And then you can solve the integral using these integral identities that I believe Florence is going to give you for the test. So you're going to know how to apply those when you need to. And then a good way to check yourself on these is to use common Gauss's law problems to see if it makes sense. So if L goes to infinity, E would be this, which makes sense according to Gauss's law if you just made a cylindrical Gaussian surface. So that's just a good way to check yourself. And then a similar problem is this disk of charge, where again, you're going to find the vector from the charge density to a reference point, and then you're going to find the magnitude of that vector. And again, you're going to see what the symmetry causes to cancel out. And then you're going to integrate, in this case, r from 0 to the radius and theta all the way from 0 to 2 pi. Another good thing to think about when you're setting up these integrals is what things you're integrating across. So if you're integrating kind of just a line of charge like this, and you're trying to find the electric field on the axis vertically, you're going to be integrating around theta or phi, whichever one he calls it, and the R and Z are going to be constant. And if you're integrating over something like a cylinder, the R is, and it's like a hollow cylinder, the R is going to be constant, and then phi is going to be varying. Sorry about my handwriting. So when you're setting up these integrals like that and creating your bounds, just think about which components are changing and which ones aren't. So back to here. In this case, we're integrating with respect to the angle around and the radius, and then use another one of these integral identities and solve for that. And again, checking yourself with Gaussian surfaces. If the radius goes to infinity and you have an infinite plane of charge, then this would simplify to that. And that's how you know that you're on the right track. So then lecture 4 was when you got into Gauss's law. And Gauss's law is when the total flux through a surface equals the total charge enclosed by the surface and then divided by E naught, or epsilon naught. And a note about this equation is that sometimes to get Q enclosed, you're going to have to do an integral if you're starting with any kind of charge density. So these are just 3 kind of key uses for Gauss's law. So if you have a point charge, you just make a Gaussian sphere. And these are usually going to simplify to these equations like 4 pi r squared, which you know is just the surface area of a sphere. And it's always going to be pretty easy to solve that around to get the electric field. And this happens to match Coulomb's law. And then if you have a sphere of charge, that's not a conductor, so the charge is evenly distributed through the volume. You're usually going to have to do multiple integrals, like one inside of the shape, where the charge that's enclosed depends on the radius. And then you'll have to do another integral outside of that shape, where the Q enclosed is the entire shape. So you're just going to have to adjust the Q enclosed side of your integral to reflect that. And then for a line of charge, you do a cylindrical Gaussian surface, where you plug in the surface area equation for a cylinder, and then solve around for electric field. And this can also work for thicker lines of charges, where you may have to do the same thing where you split up the integral again. Another important electric field to know is between parallel opposite charged plates. So in this case, the Gaussian surface that I chose was 2 infinitely long planes to the side of one side of the plate. So you're going to integrate the left side of this Gaussian surface and then the right side of this Gaussian surface and add them up. So when you do this, you get that the surface density times the area divided by epsilon naught is the total electric field going out of the plane. And just by looking at the problem, you know that half of that is going to the left and half of that is going to the right. So you can split that into the electric field being positive or minus the surface density over 2 epsilon naught. So that's half of it going to the right, half of it going to the left. And then to find the electric field total for this whole problem, you draw the arrows here for the positive plate and here for the negative plate, and then you add those up. So on the left side over here, you have this arrow, and then this arrow also applies over here. So from the negative plate, you still have this electric field going here, and from the positive plate, you still have this one here. And when you add those up, these will cancel, and then there's two arrows going to the right between the plates. So the electric field between two parallel opposite charged plates is the surface charge density over epsilon naught, and it's going in the positive x direction. And this will apply to capacitors, which is really important. And then there was a note about conservative fields, which is just for any closed path C in a field. And then another interesting problem to think about down here is if Lorentz happened to give you a volume charge density or a surface charge density or linear charge density, that was an equation in itself. So like here, the volume charge density depends on the radius of the sphere. So as it's getting further out towards the outside of the sphere, the density is getting higher. And in that case, you're going to have to add a big integral to the right side of this equation. And that's just something to think about. You can look at this example a little bit more later. It's just possible. It's a possible way for him to create a difficult problem for your test. The next thing I talked about was electric potential. And that means that to move a charge from point 1 to point 2 in an electric field, that will require a certain amount of work, and it will equate to a change in electric potential. So this is the main equation that you'll be using for that. And when you're using this equation, the V12, like the R12 from earlier and F12, that can get confusing as to the direction of it. So make sure that when you're using this equation, you assign a point 1 and assign a point 2, and make sure that all three parts of this equation match up based on what you assign to be point 1 and point 2. And then at the end, you're going to check that the electric field is what's pointing to what you found to be the lower voltage point. And then to find E from V, if you're given V in a problem, you do this equation right here, which seems like something that he's been liking to ask on the homeworks, so you might want to keep that one in mind. And then this is an example of finding the voltage across a capacitor or some parallel plates. So in this case, I assign this to be x is 0, this to be x equals d, and that's the distance between them. I'm assigning this to be point A, this is point B. And then the electric field is pointing down, and we're integrating the electric field upwards. So we're integrating directly opposite to where the electric field is going. And the voltage from this source here is the same as the voltage that's being dropped across these plates. So in the last problem, we derived this equation for the electric field here, and we're going to plug that in to VAB. VA minus VB equals the integral from 0 to d of that electric field. And then we say that the voltage at A is 0 because that's the ground node of this capacitor. And then we solve this to get that the voltage between them is the surface density times d divided by epsilon naught, which is a useful equation for a capacitor. The next thing is some properties of conductors. So in a conductor material, there's no charge on the inside. The charge can only collect on the surface. The electric field, and therefore the D field inside, is always equal to 0. And outside on the surface of that conductor, the electric field is all normal to the surface. And there can be no tangential component, which also lines up with the boundary conditions that y'all learned. So 3 important equations here. The electric field normal to the surface is the surface density divided by epsilon naught. The tangential component, of course, is 0. And then the potential in a conductor is the same everywhere, so it's all equipotential. Another example problem here is some concentric conducting cylinders. So here we're just finding the enclosed charge in each portion of this. And we have surface densities at each location on here. And they're all 3 radii. So for the radius being less than a, that's inside of a conductor, so the enclosed charge is 0, and the electric field is also 0. And then in this empty area between the 2 conductors, the enclosed charge is the surface charge 1 times that area on the surface of the cylinder. And then you can solve with Gauss's law for that electric field. And then between B and C radius, the electric field has to be 0 because that's inside of a conductor. And then you can match up the surface charge on the inner conductor and the inner charge on the inner surface of that second conductor. So using that property, you can kind of solve for the relation between those 2 surface densities. And then, of course, at a radius greater than C, the enclosed charge is just going to be what's on that outer cylinder because the 2 inside canceled out. The next topic was the dielectrics. So these are materials that polarize on a molecular level to give you some more interesting electric properties. And at this point, we brought in the D field, which is equal to the epsilon coefficient times the electric field. And this gives a modified version of Gauss's law. And an important thing to note in problems is that the D field does not change in the presence of dielectrics. So if you have an electric field going through multiple dielectric materials with different constants, the D field is going to stay the same and the electric field will change. So this is an example of that right here, where we have just 1 point charge here and then a few dielectric shells around it. And using Gauss's law, we solve for the D field, which is going to be the same everywhere going through every layer of this. And then for each section of it, we can divide that D field by the epsilon of the area that it's in. So for this area it changed, for this one changed, and it's just different for all of them. The next topic was some boundary conditions. So this is when you have 2 different materials that are lined up right next to each other, and that causes some different properties in the electric field and D fields along that boundary. So in all cases, for the normal components of that E field and D field, D1 normal minus D2 normal is going to equal the surface charge density, and E1 tangent is going to equal to E2 tangent. And that is going to apply in all conditions, but then we can narrow that down to 2 specific conditions. So if we have a dielectric boundary and there's no charge at that boundary, the surface charge density here is going to be 0. So you can just say immediately that D1 normal is going to equal D2 normal, and then E1 tangent is still going to equal E2 tangent. And then if we have a dielectric conductor boundary, there is going to be a surface charge, but you know that the electric field and D field inside of this conductor are going to be 0 because of conductor properties. So the E1 tangent is going to be 0 outside of that, which matches up with that conductor property from earlier, where the electric field is only normal to that conductor outside of it. And then we can also calculate that the electric field on that normal is the surface charge density divided by the epsilon coefficient of the area outside of that conductor. This was an example that I thought to bring up based on the last homework problem on homework 4, where he made you solve for two capacitors in series. So here I made a demonstration of kind of the same thing, but the two capacitors are in parallel. And here you're going through the process, just like you did on problem 9 of homework 4, to find the equation for when you're adding up these capacitors in parallel. So you use boundary conditions for this again, where you have, there's this boundary down the middle where you have the dielectric 1 on this side, the dielectric 2 on this side, and then on the left side it has this area, on the right side it has this area. So from this property up here, we can say that the D field on this side is equal to the surface charge, and the D field on this side is equal to this surface charge. And then we can solve for the two electric fields here. And because of the boundary conditions, where E1 and E2 are the tangential components to this boundary, we can say that they're equal. And then if we're solving for the voltage from one of these plates to the other, we integrate from 0 to D with respect to Z of that electric field, which equals the surface charge density of 1 times the distance divided by epsilon 1. And if we apply this boundary condition here, we get that that equals the surface charge density 2 times the distance divided by epsilon 2. And then we add up the total charge on the upper plate, which is the surface charge 1 times the area 1 plus the surface charge 2 times area 2. And then we use the equation C equals Q over V, where we plug in this one and then the voltage that we solved for earlier. And then we can separate out that fraction. And because we know that this equals that, we just plug that in over here, cancel some things out. And then we've solved that two capacitors in parallel equals C1 plus C2, which we know is right from just regular circuit things. And then the last thing I went over was energy storage and work, which just had a few things. So we know that capacitance is equal to the charge over the voltage. The energy stored in a capacitor is 1/2 CV squared. And then for some discrete charges, you can add up the work that is stored by assembling them, which means like the work it takes to bring in all of those charges from an infinite distance. And one example problem here of that is calculating the work that it takes to have all of these charges together at these distances from each other. So a process that I think about when I'm adding these up is you start with just this one charge here, and then you add what it takes to bring this charge 2 here in from infinity. And then you add in what it took to move this charge 3 in from infinity closer to these two. So when you have just the first charge, the work that it took is 0 because it's just there by itself. And then when you're adding Q2, you add in this term of the charge that you're moving in times what exists from that charge that's already there, which is Q1 over 4 pi E naught times the distance that it got moved to. And then when you add Q3 in, it's the same as this, but you multiply it by that term for this charge that was already there, and then add in that times what was there for this charge that is there now. So it's just kind of a process of adding these all in order, which you can think through that, or you can use this kind of formula where you sum up every combination of 2 points. Yes, these notes will be posted in the Discord as soon as I'm done. So you can reference those there whenever you'd like. So you're going to add up every combination of 2 points, and then this R is going to be the distance between those 2 points. And you can apply that to any number of these charges that are put anywhere in that plane. And then for not discrete charges, if you have some distribution, you can just do an integral of the force over a distance when you're bringing a charge in from infinity. And then I noticed that Florence didn't really give y'all a specific formula sheet that I've seen yet. So I have this formula chart from my class last year, which just has pretty much everything that he thought was useful. Y'all can probably ignore this part because I don't think y'all talked about current at all. And this boundary condition here is also not going to apply if y'all didn't talk about current. And this also has some helpful integrals. And then the gradient, divergence, curl, and Laplacian stuff. So y'all can just copy whatever you want from here onto your own equation sheets that you get to take into the test. And then a few more things because y'all do get to write your own formula charts to take into the test. Some things that I personally would try to put on those is any homework problems or examples where you're finding just an E field from any kind of distribution. So some things that I would want to remember. I don't think you should be scared of Poisson's equation. It wasn't something that my professor ever really used again. He kind of just mentioned it once. I'm not going to say like for sure that Florence won't make y'all use it, but you might want to know it just in case. And if you have some space on your formula chart, just put it there. But I wouldn't be too scared of it. So some things that I would put on my equation are some E fields from any common shapes. And the process of how you solved those. So that just means like maybe if you used Gauss's law to find the E field around a point charge, just if you want to remember how to use Gauss's equation, or something like if you had this linear distribution of charge in a circle and you had to find the E field along the z-axis, just the process of how you got to that might be useful to know. Or like if you had a semicircle of charge and you had to find the E field going this way, or just anything like that. Those are usually pretty hard to do the integrals for and to find all of the vectors and everything. So you might want to write down just a pretty good description of how you solved one of those problems on your cheat sheet, just so you can follow those steps if you run into a related test problem. And then you might want to put a little bit about solving for the voltage in any kind of interesting shape. Like sometimes I've had to solve for the voltage between like a coax cable. If you had, the ground on the outside and then some voltage on the inside. Based on the E field, you might have to solve for that. So just an example of how you'd solve a problem like that one. You might want to just think about how you'd solve for the capacitance in an interesting shape. Like if you had to find the capacitance of two spherical shells, or if you had to find the capacitance of a coaxial cable. Maybe some boundary condition problems. Just like any interesting problem that has a boundary and some E field given with some angles and some really complicated trig, because that trig can get a bit tricky, so just maybe put a worked out example of one of those problems on there, just so you can reference how you solved for those angles and everything like that. And that's about all that I have to say for this review. If you'll have any questions, you can put them in the chat on YouTube here, and I will see them and try to answer them. I'll also be holding my regular tutoring hours tomorrow morning at 11:30 to 12:30 in the IEEE tutoring room. So if you want to talk about anything in particular then, or homework 4 that's due for some of y'all tomorrow, any questions that you have, you can talk to me there. You can also message me on Discord, and any questions are welcome. I'll put these notes just on the tutoring Discord, like the main tutoring channel, and it'll just be a PDF with everything. So y'all can access it there if you'd like, and hopefully that helps. If you want to just message me individually and ask for them if you can't find them, that's also okay. Yeah, I would not worry too much about Poisson's equation. I mean, I don't want to promise you anything, but it shouldn't be too difficult. You just do what looks like the gradient twice, so that's just a double derivative, and you got it. I can stick around for the last 10 minutes if y'all would like to ask more questions, but you're also free to go if you'd like. That is all the review that I have for y'all today. And I wish you all good luck on your test. Y'all are all going to do great. Just, keep it simple and you will do absolutely fine.